Yeah, I think we can start. So today we are very happy to have Professor Shivaji from University of North Carolina at Greensboro, USA, in our distinguished lecture series. Title of his talk is A Comparison Result when the forcing terms are closed in L1 norm. Before that, I request Professor Kannan to say a few words about our today's speaker. Sir, over to you.
Yes, I'm happy to welcome Professor Ratnasingham Shivaji and to introduce him to our group. He received his PhD in mathematics from Heriot-Watt University in Edinburgh, 1981. His BS from the University of Sri Lanka in 1977. Then he joined the University of North Carolina at Greensboro. In 2011, he was the head of the Department of Mathematics and Statistics until July 2019. Then beginning in January of 2012, he was named H. Barton Excellence Professor. He also served earlier for 26 years at Mississippi State University, where he was honored as W.L. Giles Distinguished Professor. In 2019, he was also named a Fellow of the American Mathematical Society. He is the recipient of the 2020 Mathematical Association of America Southeastern Section Award for Distinguished University Teaching of Mathematics. Professor Shivaji's area of specialization is partial differential equations, as already mentioned. In particular, he works on nonlinear elliptic boundary value problems. His research work has applications in combustion theory, chemical reactor theory, and population dynamics. It has been funded by the National Science Foundation and the Simons Foundation. Currently, he is serving as the PI on an NSF Math Ecology grant. He has authored 160 research papers. He is a member of the editorial board of several mathematics journals, and I'm happy to welcome such a distinguished person to deliver our distinguished lecture today. Welcome, sir.
Thank you very much, Professor Kannan. Thank you very much. Your introduction definitely indicates that I'm a very old person. I've been out for a long time. So I'll try my best to present something today. Am I ready to go?
Yes, sir.
Yeah. Now you can
start. Yeah.
Start. Yeah, please.
Okay, you all can hear me, right, everyone?
Yes.
And see the slides too?
Yes, we are seeing.
Yes.
Okay, very good. So I'm going to talk about, I know that quite a few people in the audience are not specialists in differential equations. So anyway, the first half of the talk, first part of the talk at least, would be hopefully accessible to everyone, but I'll try to keep the second half also as accessible as possible. So I'm going to start with a simple calculus 1 story, even though I call it maximum principle, but this should be not too difficult to understand. If you have a function u whose minus of the second derivative is equal to some function h, let's take the interval 0 to 1 with 0 boundary conditions or Dirichlet boundary conditions at the boundary 0 and boundary 1. And u is a C2 function satisfying this equation. Suppose this right-hand side is greater or equal to 0, it is easy to see that u has to be greater or equal to 0 because your second derivative is negative. The function is 0 here, the function is 0 here, the second derivative is negative. So one can easily see that the shape of the function u has to be like that. It has to be greater or equal to 0 on the interval 0 to 1. So I think this is fairly easy to understand. So based on that simple observation, we can come up with a simple comparison principle. Suppose now you have an inequality with two inequalities or two equations, if you want to call it. So you have a function u1 such that minus u1 double prime is greater or equal to some h1, still satisfying the Dirichlet boundary conditions. And another function u2 such that minus of u2 double prime is less than or equal to h2 on the interval 0, 1 with the same Dirichlet boundary conditions. And then if you have orderedness on the h1 and the h2, if the h1, the right hand side h1 here is always greater or equal to h2 on the interval 0, 1, then one can easily deduce that this function u1 has to be greater or equal to u2 on the interval 0, 1. So this just follows from the previous slide that I talked about of the simple maximum principle, or whatever you want to call it. So the proof is fairly simple. So you take a function u, which is the u1 minus u2. This is the typical way of showing. People who are working in differential equation, they'll always do that. If they want to show that u1 is greater or equal to u2, then define u1 minus u2 as u and see whether it can satisfy some sort of a maximum principle to give you that story. So if I take u to be u1 minus u2, then one can easily see that minus u double prime is minus u1 double prime plus, because of the minus there, plus u2 double prime. So the minus u1 double prime is greater or equal to h1, whereas minus u2 double prime is less than or equal to h2. So u2 double prime has to be greater or equal to minus h2. So one can easily come up with this inequality. But since I already assuming here that h1 is greater or equal to h2, then this would be greater or equal to 0. Since u1 and u2 are 0 at 0, u will also be 0 at 0, and you will also be 0 at 1. So you see that the difference between u1 and u2, which I called to be u, is satisfying exactly what we talked about in the previous slide. Minus u double prime is greater or equal to 0 on the interval 0, 1 and Dirichlet boundary conditions. So that means u would have to be greater or equal to 0 throughout the interval 0 to 1, which implies that u1 is greater or equal to u2. So this is a very simple comparison principle that we can come up with when you have a set of equations like that. Okay. So the story today, a simple story that I'm trying to tell today, is that what if we do not have this? What if we don't have h1 is, of course, if you have it, that's well and good. But what if you come up with a situation where h1 is not greater or equal to h2 throughout? We don't have that information satisfied, but at least we know to some extent that in the L1 norm, well, L1 norm of a function is nothing but that, the standard definition. But at least in the L1 norm, these h1 and h2 are very close. Can you say something about u1 and u2? So this is going to be our set of two equations that we are going to be talking about. So you have minus u1 double prime greater or equal to h1, and minus u2 double prime is less than or equal to h2. But the problem is that we do not have this condition anymore. Instead, we are going to be looking to see what if in the L1 norm, h1 and h2 are close, right? Then can you say something about u1 and u2? That's the story for the day. So it will be a very small story that I will try to say today. Okay, so here is the theorem that we will try to, I'll try to talk about. So these functions h1 and h2, I'm going to assume that they are L1 functions. But I want to assume one story here I'm going to assume that my H2 at least is greater or equal to 0 and it's not equal to 0. Remember the H2 is the second equation here. This function, I'm going to assume that it's greater or equal to 0 and not equal to 0. So in that situation, what we will like to prove today is that given an epsilon between 0 and 1, I can always find a delta such that provided the difference in the L1 norm, H1 and H2 in the L1 norm is smaller than that delta, then you can at least get this comparison between U1 and U2, namely U1 has to be greater or equal to 1 minus epsilon naught times U2. So that's the theorem for the day. So not too much. I hope that will basically this comes out from a. Let me just emphasize something, and I have put the entire. I have provided the entire talk to the organizers so they can share it with you all as you all need. So this really comes out from a certain paper that we talked about in terms of some P. Laplacian problems on exterior domains, which reduces to a little bit more complicated problems than what I'm talking about today. But I'm extracting just the case when we are not dealing with the P. Laplacian, just the Laplacian, just to give you all the idea what's going on here. So that's where this story is going to be applicable later on, which I will talk about a little later. So I've really extracted kind of a U double prime version of this of the idea that was used in that particular paper, in an important sector of that particular paper. Okay, so that's what we have. So that's the theorem one more time. That's the theorem that we want to prove, that if H1 and H2 are L1 functions with H2 greater or equal to 0 and not equal to 0, given any epsilon, you can always find a delta so that you can compare U1 to be greater or equal to 1 minus epsilon times U2, just a little less. Okay, so how are we going to, let's first of all make a plan for the proof. Okay, let's define new functions V1 and V2. They satisfy equality. Remember, your U1 satisfied minus U1 double prime is less than or equal to H1, and with Dirichlet boundary conditions. But I'm defining a function V1 that satisfies equality. So maybe I should put that in a different color. That's not too much of a different color, so let me try. Okay, and similarly, I will also define a V2 which satisfies equal to H2. Remember, your minus U2 double prime is less than or equal to H2. And of course, okay, so if I just look at this U1 here and the V1, it's very simple to say, same argument that I used earlier. If I take, it's easy to compare these two. Minus U1 double prime is less than or equal to H1, and minus V1 double prime is equal to H1. So now if I use the simple comparison principle that I talked about earlier, you remember? The comparison principle that I talked about earlier was, so in this particular case, when H1 is greater or equal to H2, then of course you can compare them very fast. So here also, ladies and gentlemen, here it's the same H1. So they can be compared. So if they can be compared, then you can realize that very fast from the comparison principle, this U1 here has to be greater or equal to this new V1 that I'm talking about. V1 is the one which is equal to H1. Similarly, one can look at your U2 and your V2, again, we are working with the comparable functions here. So it's very easy to see from the earlier comparison principle that the V2 function is to greater or equal to U2. So we were trying to prove that U1, I'm sorry, my dog is making noise. I'm sorry. 1 second, 1 second, please. Mom, that's too much noise. I'm giving it. Sorry, please. Can you put him outside also, please? Sorry about that, ladies and gentlemen. Okay, so since we know that U1 is greater or equal to V1 and V2 is greater or equal to U2, and you were trying to show that U1, you were trying to make a comparison between U1 and U2, U1 was greater than 1 minus theta time, 1 minus epsilon times U2. Well, if we can prove it between V1 and V2, then we are done. Because, so if we can show that V1 is greater or equal to, for a given epsilon naught, there's a delta such that V1 is greater or equal to 1 minus epsilon naught times V2, that will be fine, because then the U1 we know is greater or equal to V1, and V2 is greater or equal to U2. So then that means we'll get the inequality that we are looking for between U1 and U2. Would that be okay, everyone? So we will forget about U1 and U2 now and start working with these functions V1 and V2, which satisfies equalities. Okay. So the big question has now been reduced to simply the following question. Is V1 greater or, given an epsilon naught, is there a delta such that if H1 and H2 in the L1 norm is smaller than that delta, can we compare V1 and V2 in this manner? V1 is greater or equal to 1 minus epsilon naught times V2. So that's the story that we are going to be aiming. Okay, so first, let's compare its derivatives in the sup norm. So we will prove that given an epsilon, there is a delta such that if H1 and H2 in the L1 norm is smaller than delta, the V1 prime and V2 prime in the infinity norm is smaller than epsilon. That's what we will first prove, and then use that to eventually get to this particular step. And you know that if I get to that particular step, then we do have the inequality with U1 and U2 as well. Okay, so remember, minus V1 double prime or is equal to, or Vi double prime is equal to Hi, because we are now working with the equalities. The Vi's are satisfying equalities. Let me take a sip of water or coffee. So, and also we know that the Vi's are satisfying the zero boundary condition. So one-step integration of this equation using the fact that Vi of 0 is equal to 0 gives you this story here. So you're just integrating both sides from 0 to t using the fact that, but well, no, I'm sorry. I think I made a mistake there. So not yet. So I'm just going to integrate this equation from 0 to t. So I get Vi prime of t minus Vi prime of 0. That is what I have called here as my Ci. Then I get that story here first. So that's a simple integration of this differential equation. And then if I integrate it again from 0 to 1, if I integrate it from 0 to 1, then I get on this side, I'll get 0 minus 0, because Vi of 0 is also 0, Vi of 1 is also 0. Then from there, I can easily see that integrating this, just that Ci would be just nothing but this story here. That's very easy to see. So that means this is true for C1 as well as C2. So if I take the absolute value between C1 and C2 from these expressions here, it is easy to see that you can bound that by the L1 norm difference between H1 and H2. So just to write it down, and take the absolute value and push it inside, and this won't be too difficult to see. Okay, so that means what is my, going back to this equation here, what is going to be the difference between v1 prime of t and v2 prime of t? Okay, so just taking the difference using this particular formula, taking the absolute values, it will be less than or equal to the absolute value of c1 minus c2 that is coming from here. And then here, of course, you have to write it from 0 to t, from h1 minus h2, and take the absolute value. That again, you can easily bound it by the L1 norm difference of h1 minus h2. But then this part here, I have already showed you that that is also less than or equal to L1 norm difference between h1 and h2. So all these stories here will become less than or equal to twice that story. Well, that's good enough to always prove this. So once you have, ladies and gentlemen, this estimate, if you control this one, you can always control that one. So that's how this lemma is established. Is it okay, everyone? So that's a fairly easy establishment. Okay. Now let's specifically work with my V2 function. Remember my V2 function. V2 double prime is equal to H2 on 0, 1. Here, remember, we assume that this H2 is greater or equal to 0 and not equal to 0. Because of that, one can prove something on V2. The V2 is always greater or equal to the sup norm of V2. Well, you know that this function V2, because this is greater or equal to 0, you know that this function V2 has to have that shape. Because it's 0 here, it's 0 here. This is greater or equal to 0, so it's a concave function. But we can prove something more, that this V2 of t at any particular t, V2 of t has to be greater or equal to the sup norm of V2. At sup norm, somewhere it must be some ht0, I think it must achieve its maximum. That maximum times p of t is the distance function to the bound. P of t is the minimum between t and 1 minus t. This you can prove because the h2 function is greater or equal to 0. You can do that. One can go back and
Professor Shivaji.
Yes, sir. Is that more?
It seems there is a question in the chat box, but due to my internet connection, I'm not able to see it. Could you read out the question and answer? I'm not able to in the chat box.
Suppose you have Neumann boundary condition, then what can be said about the minimax principle? I'm not talking. So okay, I don't know. I have to. I'll check on that, but I'm not specifically. What is that you're asking me? Can they speak up? I can only. Well, you know, you can also extend these maximum principles to Robin boundary conditions, but with Neumann boundary condition, one needs to be very careful because you have these constant solutions that can be solutions.
Hello, can you hear me?
I can hear you.
Yes. Suppose you have Neumann boundary condition. So I mean a problem with Neumann boundary condition. When it is Dirichlet, that is fine. Right. But for Neumann, something can be said about comparison principle. I mean, something can be said about minimax principle.
You got to be careful with Neumann boundary conditions because constants are solutions there. A constant function could become easily a solution. Say, for example, if you have, so I think you've got to be a little bit more careful. So you have to, I mean, you can do something if you have, rather than having, say, minus u double prime, say, suppose you have minus double prime plus C of U is greater or equal to, you know, if you have something like this, then there are comparison principles that you can easily build. But otherwise, I would not try to make a blanket statement right now. But, you know, if you want to learn a little bit more about this, you can go ahead and look at the book of The Maximum Principle by Protter and Weinberger. It's a classical book on maximum principle where they will talk about many things that you might want to find.
Okay, thank you.
Does that answer your question? So I won't, I'm concerned. What I'm talking here about Dirichlet problems and probably Robin boundary conditions work very well for the maximum principle. But, you know, with the Dirichlet Neumann problem, you could be always a little careful. But, you know, if you have a term like this, then things, there are a lot of things on the maximum principle side. Is that good enough for the answer for the time being? We can talk about it later.
That's fine. That's fair enough.
Thank you.
Okay.
Okay, good. So how do we prove this? How do we prove this? So that's not too difficult also, because you say that your minus V2 double prime is equal to H2. So it's very easy to integrate the equation just like what I did earlier. Just that I integrated it from 0 to t. And if I integrate it even further using this boundary conditions here, I can come up with the V2 of t. That means I'm integrating this again from 0 to t. That means I'm only using this boundary condition here. And then I get V2 of t would be, this is what I'm calling to be C. Well, I've switched the signs a little bit, but it's okay. If I do some integration, so I get the C times t, and then I have to integrate this guy. This guy has moved to the other side here. So I get something like this. And now if I look at this integral, I'm sure you must be teaching this very much in your calculus. I can change the order of integration. If I change the order of integration, right, in this triangle here, then I can write this as the integral from 0 to t and z to t. And then, of course, now this becomes independent of s. So then this becomes, the integrand becomes just the integral from 0 to t, h2z's times t minus z. It's a standard change of changing the order of the integration in this double integral. And then that double integral can be just written like this. So what does that mean? That means my V2 of t would be this minus C of t times this double integral now written that way, we'll have that. Now, if I know that when t is equal to 1, this V2 is again 0, so that means I have my C. I have my C is just nothing but 0 to t of course, t is 1 here. So that story there. So what is V2 of t? So here is my C, which I have here, multiplied by this t. That's what I have here. Minus this integral that was always there. So ladies and gentlemen, once again here, this is the integration from 0 to 1, this is the integration from 0 to t. So you can split this integration from 0 to t and from t to 1. So the t to 1 part, is here. So when you do this from 0 to t, so I have another 0 to t here, so I combine it together. If you do the calculation here, it's very easy to see that this is z times 1 minus t. So at the end of the day, for these types of problems, so some of the people in the audience, this is very simple, but still, since I'm not very sure others would have seen it, so I'm just going through the calculations here. So the V2 of t will become 0 to t, z times 1 minus t times h2 from 0 to t, plus from t to 1, it will be t times 1 minus z. Z times 1 minus t and t times. So this is, one can write this in a combined manner, that V2 of t is the integral from 0 to t of this function g of tz times h2 of z dz, where this g of zt is the split function. If the z is less than t, it is z times 1 minus t. If the z is more than t, then it is t times 1 minus z. This is what they refer as the Green's function that you may have talked about, you may have heard. So, but I'll leave this as a simple exercise, but you can show that for any t tilde between 0 and 1, this is the explicit function here. Right? You can show that for any t tilde between 0 and 1, this ratio, so g of t z and g of t tilde z, is always bigger than the distance function p of t for any t z and t tilde between 0 and 1. I don't think that's too difficult to see. You can go and calculate that. Okay, so with that in mind, let me remember never forget what we are trying to do. What we are trying to show is that for these types of functions, I will be using this again later on. For these types of function, when this side is non-negative, using this Green's function idea that we have here, we are going to be able to show that the v2 of t is bigger than the sup norm of v2 of t times the distance function. So basically, we have come to the point where my v2 of t was 0 to t. That was what we derived a few minutes ago. So let's assume that this t naught, you know that the v2 function is like this. So there's some t naught in between where it's getting the maximum. So this g function is positive, so I can divide and multiply. But then this story here is bigger than or equal to p of t, which is independent of the z. So it works out. So then you have p of t times the integral from 0 to t of g of t naught z g of t. But g of t naught that's just like putting t naught here. It's that v2 of t naught, and that is exactly what the sup norm of v2 is. I'm sorry, I'm messing up here. Sup norm of v2. So that's it's just an integration. Just a proof to show that this v2 of t is in fact always greater or equal to the sup norm times the distance function. Okay, so we have two stories that we are dealing with. We know that given an epsilon, there is always a delta where we can compare the infinity norms between v1 prime and v2 prime, or control it less than epsilon by taking h1 minus h2 in the L1 norm less than delta. And then we also have made the observation that this v2 function is always greater or equal to the sup norm of v2 times p of t. So now we'll get to the proof. And the proof, let's remember what we are trying to prove. We are trying to do a comparison between v1 and v2. That's what we are after. Given an epsilon naught. So an epsilon naught has been already given. Okay. So once again, so this is what we are after. Epsilon naught has been given. So let me start off with an epsilon smaller than this quantity here. Now, if I use my lemma 1, there is a delta such that if this L1 norm between H1 and H2 is less than delta, then one can compare the V1 prime and the V2 prime in the infinity norm. We know that. Okay. But then let's see what is V1 minus V2 is. Remember, V1 minus V2, well, of course, this is just calculus 1. They are both 0 at 0. V1 of 0 is also 0. V2 of 0 is also 0. So by the fundamental theorem of calculus, this has to be true. But because of this story here, I can always bound this by greater or equal to minus epsilon. because in sup norm it is less than epsilon, so I could always bound v1 prime of z minus v2 prime of z to be always greater or equal to minus epsilon. So that means this integral will turn out to be greater or equal to minus epsilon times t, right? But I could also write v1 minus v2, since this is, I'm writing it because v1 of 0 is 0. By using the fact of v1 and 0 is 0 and v2 of 0 is also 0. But since v1 at 1 is also 0 and v2 of 1 is also 0, I can also write v1 minus v2 as the integral from t to 1 of their derivatives, right? It's fundamental theorem of calculus. But again, since this estimate is there on the sup norm between v1 prime and v2 prime, again, this part I can bound it by minus epsilon from below. So that means this integral is also greater or equal to, this integral is greater or equal to minus epsilon times 1 minus t. Well, of course, if you just flip, if I just take all the minus, if I just look at these inequalities the other way around, so v2, this means my v2 minus v2 of t minus v1 of t will be less than or equal to epsilon times t. If I just, and similarly, v2 of t minus v1 of t would be less than or equal to epsilon times 1 minus t, just multiplying by minus sign. So that means this story here has to be less than or equal to epsilon times the minimum between t and 1 minus t. So that's your p of t. This is, remember, this guy is the minimum between t and 1 minus t. Okay, so that means my v1 of t in particular, if I flip this, has to be greater or equal to v2 of t minus epsilon times t of t. Okay, everyone doing okay there? So, but remember your epsilon. I chose my epsilon to begin with to be less than epsilon naught times the sup norm. So that means I can put something bigger here to make it even smaller. I replace my epsilon by epsilon naught times the sup norm of v2. So that means the inequality will go nicely in this way. That's bigger. But then, so this is v2 of t and then here. But then you know that your v2 of t, remember we proved that in lemma 2. v2 of t is always greater or equal to the sup norm of v2 times p of t. Right, we proved that. So this part here is actually smaller than v2 of t. So if I replace this by v2 of t, that means the inequality will go in the proper way that way. That will be even smaller. And that's exactly what we want to prove. Once you do that, then this becomes 1 minus epsilon naught times v2 of t. So we achieved what we want to prove in terms of v1 and v2. And as I mentioned, once you prove it in terms of v1 and v2, your u1 is always greater or equal to v1, and v2 is always greater or equal to u2. So that means we'll get the theorem that we wanted to prove. As long as h1 minus h2 in the L1 norm is controlled, then we can always achieve that inequality. Okay, so that's a proof of the simple theorem that I wanted to talk to you all about today, which of course is nothing but a little bit of calculus and a little bit of story about that v2 function. So for the rest of the talk, why did we even think about this? Where are we using this? So I'm going to talk about an application of this inequality that we had, or why did we think about it, or why did we have to come up with that? So as I mentioned to you, this comes from a problem that we started studying. That's a boundary value problem that really, of course, P Laplace inversion is there, but let's look at the Laplace inversion of the problem for the talk today. You can read the P Laplace inversions in the paper that is attached to this slides. So let's look at a boundary value problem where we are looking for positive solutions of this nature. So again, minus u double prime. Well, today is all lyrically boundary conditions. I'm not talking about anything else here right now. So the right-hand side has the nonlinearity or the reaction term split in two ways, an h of t times f of u. So this is when you come from exterior domain problems, do some Kelvin transformation, even with the general f of u, some out of this h of t terms comes in, and often it is a singular function at 0. So usually this h of t, an example of this h of t is like this, between 0 and 1. But in particular, the interest in this particular paper that we started studying is about a case of a what is referred in the literature as a infinite semi-positron problem. Don't worry so much about that today. I mean, the audience, I know that you all are not expert, but anyway, this f of u here is a singular function. Not too bad. It's singular in a certain manner. It goes up to minus infinity at 0, and then eventually it becomes positive. Typical examples are here. Even though it's singular, later on they have some control. Singularities have control. So for problems of this nature, the differential equation commentary, or many of us, I think there are people in the audience here as well who are interested in these types of problems. Usually this is going to be a sublinear function at infinity. That means for large S, this function is going to grow slower than a linear function. For those types of problems, there's been a lot of interest in proving existence of a positive solutions for large lambda. Okay? I won't be talking about it. But then even further, there's always an interest about talking about uniqueness of this positive solution for large lambda. I won't quite talk about this today, but that's what the paper talks about. But to prove this uniqueness result for large lambda, it is extremely useful to understand how the solution grows for large lambda. Is there a priori estimate of the solutions that you could assume for large lambda? Namely, can you show that u of t, which we know is existing, is greater or equal to some constant, this is a constant, is lambda times the distance function. Lambda is in the equation. Lambda is a parameter in the equation. So is it possible, I don't know why this happened that way. Does anyone know how? Okay, there. So is it possible? So here is the problem. So all you all are, for this particular talk today, all I want you all to concentrate is the following. So you have this problem with some singular parts of the reaction, some singular terms, it doesn't matter. There's a parameter lambda here. There's a parameter lambda here. We know that the solution exists for large lambda. Can we show that solution grows faster for large lambda, grows faster than a certain constant times this lambda times the distance function? So that's the focus. This information is heavily used at the end of the day in proving that the solution for large lambda is unique, and I would leave you all to enjoy reading that in the paper. But today I'm just going to show you, even in this difficult situation where f is changing sign and also coming from infinity, how the previous comparison principle that we talked about is going to be helpful to show you this growth, priori growth. So that's the focus. When I say application, that's the focus that I'm going to be talking about for my rest of my talk, which is time is running out. I guess till what time do I have? How much more time do I have for this talk?
Yeah, you can continue, sir.
Okay, good. Good.
Yeah,
I won't keep you all too late. I know that for me it's morning, but for you all it is evening. Okay, So I'm going to, once again, so this is what I'm going to prove. I'm going to try to prove this, or try to show you all how I use the previous story to prove that. So once again, the given function f, I know it's a singular function, but the singularity at 0 is not too bad, so that this function exists. That means the singularity, even if it's going down, here it doesn't go down faster than some sort of a s to the alpha or minus 1 over s to the alpha, where alpha is control, alpha is small enough, so that if you define the primitive function, that primitive function is well defined. Actually, the primitive function would be existing, and it would be up to beta, it will be decreasing, and then it will start increasing, because up to beta, you know that capital F prime is small f. So up to beta, capital F was negative, so that means small f was negative, so the capital F is decreasing, and then it increases. So you have a unique theta in which this capital F function becomes 0, and then of course the capital F is positive. Let's not go into any of these details, because those I'm sure you can read it in the paper, that attached paper. You can show, ladies and gentlemen, you can show if a solution exists, the solution must have this particular shape. That means it is going to increase up to some value. I don't know what you want to call it, P0 or something like it. It starts at 0, it will increase, of course, less than beta. Your small f is negative. H is always positive. Small f is negative, that means u double prime is positive. So I think the shape of the solution would be up to beta, the solution would be like that. And then it will start turning around. So anyway, so the shape of the solution can be proved to be something like this. I will not talk about that because of time constraint. So I take a rho value between these two numbers, beta and theta. So that's a rho value where small f is positive, capital F is still negative. Okay? So basically I take it as rho theta plus beta by 2. So this again, today's lecture, I won't be concentrating on that. This is called a boundary analysis. How does the solution behave near the boundary? These are the boundary, right? The boundary is 0 and the boundary is 1. How does the solution grow near the boundary? Again, the step 1, this has nothing to do with the application of my result today, but you can prove that this function in these sectors, in this sector as well as in this sector, I can show how it goes. So that part, I would again request you all to read from the paper. It does not have anything to do with this comparison principle that I talked about. So basically what is happening in these sectors, U is growing in the form great right with some C times lambda to the some power 1 over 1 plus alpha. Alpha is a number between 0 and 1 times this function. These functions exist. I'm going to assume that H is L1, then you can show that. Similarly, again in this sector, again, similarly, this function U of t is great rho equal to lambda times C times some constant C times lambda to the 1 plus alpha times this function. So those things, once again, ladies and gentlemen, I'm going to, they are proved in the paper attached. Now, what this tells us is something very important. That means these guys, the points where the solution hits this value, that is that fixed value theta plus beta by 2, that is one is T rho and one is T rho tilde. Because of this estimates, it's easy to see that the maximum between these guys is less than or equal to maximum between T rho and 1 minus T rho is less than or equal to some constant times lambda to the minus half. Basically, what it means is that when lambda gets bigger and bigger, these guys are going towards, T rho is going to go towards 0 and T rho tilde is going to go towards 1. So that's another conclusion that can be derived from this estimate here. So you can understand how the solution is behaving. So this is a kind of a little bit of a boundary analysis, how they are hitting this particular value. and how these points are moving when lambda gets bigger and bigger. You can see if lambda gets bigger and bigger, this is going to go to 0. That means this maximum is going to go to 0. So all that, ladies and gentlemen, I'm not going to talk about today. Please do put that in the paper. So now with that information in place, always be focused on what we are trying to achieve. With all that information, the focus is trying to prove this part, the growth of u of t throughout. This is throughout the interval. How is the solution going? Okay, so that's from the boundary information. We now go global. That's where I'm going to use this comparison principle that we proved. Okay, so all that is information is there. But when u is bigger than rho, that is the complementary interval. So the solution, if I go back to the solution in this interval, u is more than rho. U is more than rho means you remember your f. F was going like that, and that's theta, that's beta, and then comes the rho, beyond rho. Okay. So when you are in this interval, you realize that my u is bigger than rho. That's one observation that I want to say. So that implies sorry. That implies you can find a delta rho such that f of u is greater than some delta rho when t is in I, because u is bigger than rho, so you're already into the positive range of there. So you can find a lower bound. F of u will be always greater or equal to some constant delta rho as long as your t is in I. So that's your first observation that I want you all to have in mind. Secondly, I'm going to assume, as I mentioned earlier, that even though this f has singularity, it is not too bad. It can be bounded by a function of, oh, that color is bad. It can be bounded by a function of that nature, like minus a over z to the alpha. There is a constant a such that f of z is always greater or equal to minus a over z to the alpha for z positive. So there's some sort of, basically what I'm trying to say is that this alpha is, the alpha, remember, alpha is just a number between, well, it's less than 0 and 1 in certain cases, but at least in 0 and 1, so you can bound it by that singular function. So then let's go back to this story here. Let me assume that, okay, I'm going to take all this. Let me assume quickly, so let's go back to these sectors one more time, if you all don't mind. In these sectors, let me assume that my lambda is big enough so that this number is greater or equal to 1. So that means if I take my lambda to be big enough, that's when I want to prove the estimate. Anyway, that means in this particular sector, I'm sorry, I forgot to do that. Okay. So in this particular sector, I can assume that u of t is greater or equal to this number, because I'm assuming that this part is greater or equal to 1. And in this sector also, I'm going to assume that u of t is greater or equal to this number, this function here. Okay, guys. So I'm going to assume that. I'm going to assume that from my step 1, since this is, if I assume that that is bigger than that, I simply get this. So now I am ready. Remember, my u double prime is lambda h of t times f of u. That's what my u was satisfied. Okay, I'll move this lambda. I'll move this lambda as lambda to the -1 times u double prime. So if I move that this lambda over here, then I can write these estimates in these different sectors. This is the hard part, and this is the only part that you need to observe, and then things become very easy. So if I move the lambda to the other side, ladies and gentlemen, like that, then I have great Y. So let's go to this particular sector. So then I have the H of T, which I already have it here, times the F of U. Remember, I'm assuming that my F of S, oh, come on. I'm assuming that my F of S is always greater or equal to minus A over S to the alpha. And you know that in this particular sector, you already assume that we already know that U was bigger than that. So I can bound this F of U by minus A over even something smaller. Then this becomes even more negative. So basically, I'm using this information and the information that the U was greater or equal to, in this particular sector, this one. So if I combine them, I have that. Are you all with me? Right, that's what I'm doing. Similarly, ladies and gentlemen, in the middle sector, okay, it's greater or equal to H of T, but I know that in the middle sector, I know that my F of U is always greater or equal to delta rho, some delta rho. Okay, so that's simple. But in the last sector again, it's greater or equal to H of T times again F of U, but in this particular sector, I have to use this story here for the U, and combining with this lower bound on the function F, I have that. Okay, so now I'm starting to look at something like my earlier story on comparison principle. So I have a certain function, minus of that second derivative is greater or equal to some h1 function. Some h1 function. It's complicated, all right. It's complicated, all right. H1 function, which I call all that to be H1. And of course, even with the minus lambda, lambda inverse, U satisfies zero condition. So this function is satisfying the zero boundary condition. Is it okay? So I'm starting to look at my comparison principle for this complicated H1 function. Now I take a very simple, like my U2 function. This is like the U1 function. So I take the function W0, which satisfies H of T is a positive function, times this delta rho, which is also a positive number. So you realize that this is like a positive function, like the V2 function that we talked about. So that's what that's what I'm going to use as my H2. But remember, this function, it's exactly like what I talked about earlier. When this side is positive, this function W will again satisfy this type of an inequality. The W of T has to be always greater than or equal to the subnorm of W of T times P of T. We did this calculation. But anyway, the bottom line is, so I'm going to use this as my H1, this as my H2. Now, if I can show that the H1 minus H2 can be controlled in the L1 norm, then I should be able to compare this function with this W function. That's the story. So that's what, okay, we can prove that these functions are in L1, with the condition. So basically, I go and look at, due to the time constraint, I won't go too far, I won't go too slow. I look at the H1 minus H2 for these two functions, guys. For these two functions, this function is H1 and this function is H2. I look at my L1 norm difference between H1 and H2. But of course, in the middle sector, both of them are the same. So in the middle sector, the difference would be 0, but you will only get the other two, where you are really so this function minus that will be a positive. So you get some sort of a story like that in the middle sector. I know I thought I had too little, but looks like I'm going too slow. Okay. So the bottom line, ladies and gentlemen, the bottom line is the following. You remember, we already had the information that this T rho is going towards 0 when lambda goes to infinity. And this T rho tilde is going towards 1, as lambda goes to infinity. So so the bottom line is that using this information here, it is easy to show that this integral, this right hand side here goes to 0 as lambda goes to 2. So that's the story. So this lemma that we proved earlier, the boundary analysis that we did earlier, shows you that I can, even though these are complicated H1, H2 is very simple, we can show that I can control the difference between H1 and H2 in the L1 norm as small as I want by taking lambda large, because I have this information on the boundary layer data. I have that information on TO and TO data. So that means now I go back to my comparison principle, taking epsilon naught to be 1/2. You remember I can compare that function and my W naught function as 1 minus epsilon naught. So I can take the epsilon naught to be 1/2, and then I know that for lambda large enough, this will go to 0. That means I can apply the theorem, comparison principle. That means I can compare this, which is actually 1 minus 1/2 is just 1/2 W naught. But remember, W naught is always, this W naught function is a nice guy. You remember we talked about it in terms of the V2. We remember the story on V2. So I can compare the W2 is W naught T is always greater than or equal to the sup norm of W times P of T. So there you go. So I can, with the W naught here, okay, I erase all this. The W naught here is greater or equal to sup norm of W naught times P of T. Okay, so if you think of this as your constant C naught, then if you move the lambda to the other side, then you achieve what a priori estimate that you wanted to achieve. Okay, so that's the story, why we had to do this. Of course, we are doing it in the Laplacian sense, so you can look at some comparison principle, the full version of the comparison principle that we proved in the paper, but I try to water it down to the U double prime case so you can have a look at it. So that's the one application that I was useful. Thank you for listening. All these things is in this particular paper in a more Laplacian version of that. And I think I have attached the paper also for you, ladies and gentlemen, and the organizers can definitely pass it on to all the participants, or if the participants wants to email me, I can also send it to you all. Thank you very much. That's about all I wanted to tell you all, and I'm sorry I'm past time, way past time.
It's okay. So thank you very much for your nice talk and the presentation. Indeed, the presentation is very nice. It looks like the classroom teaching, although you call it is old-fashioned, but it is very good. Okay.
Very old-fashioned. I'm sorry.
Yeah. But it is good to us, so it's okay. So now I'll ask if you have any question. Do you have?
I already have a chat question. Is that right? Another chat question. Oh, thank you, sir. Okay.
No. So are there any question from the participant?
Yes, Professor Shivaji, can you hear me?
Yes, Sweta, I can hear you.
Yeah, so first of all, it's a very wonderful talk. I have one question. In your f of u, okay, so you have taken the assumption that on q, that q should be between 0 to 1. F of q is
you mean the alpha?
Yeah. No, not alpha, on q, because you were having minus 1 by s to the power alpha plus s to the power q, where q is between 0 to 1.
I see. Okay, let me okay. Yeah, can I go ahead and share it back if you all don't mind?
Yeah, please.
Okay, here we go.
Yes.
I think you all can see.
Yes.
That's what you're asking me, right,
yes.
Sweta?
Yes.
Yeah.
Yes. So here you have taken q between 0 and 1. So if I'm not, if I have got it correct, that this q, the constraint on q has nothing to do here for your maximum principal. It may be because of some other reason.
Absolutely, Sweta. That is because I'm assuming this q is between 0 and 1 is exactly the story that I told you, that the growth rate here is slower than a linear function.
Yeah.
Okay. And that is used to the existence result.
Yeah. But suppose if we were having some other reason, can we expect to go?
Someone is talking. I cannot hear you, Shweta.
Hello. Yeah. I think
Someone is
somebody
overriding
yeah.
your.
Yeah, I think. Excuse me, please mute yourself. Who is that?
Okay, go ahead, Shweta.
Yeah.
Sorry for the disturbance.
Okay. It means, suppose if I'm not bothered about the existence, if I will look for the comparison, is it possible that I can take Q up to P sublinear? Means, which has been the case for P Laplacian maximum principle.
Your question is about this example, right?
Yeah, like in the not in
the comparison principle had nothing to do with the example. Number one, those were just some functions h1 and h2, right?
Okay. Yes.
So it depends on how you can, if you have a different example, how you can frame it into an h1 and h2, and those things don't have anything. Those are just right-hand sides at the end of the day.
Okay. Okay.
Did I answer your question, Sweta?
Yes,
I mean,
yes,
I really
yes.
don't know. Okay, so
No,
comparison principle is more general. I mean, that's just as I said. I like to. I thought I can talk about that because then, especially bringing it down to just minus u double prime, so that anyone who is not working differential equation also can enjoy a little.
Exactly. Means it is really for a very like general audience and very well presented. Like.
Thank you. I just want
it's always like treat.
But you won't see this in the paper though. Paper has the more complicated P Laplacian version of that. So the differential equation people who are interested can read the comparisons principle there. So when you are working with the P Laplacian,
yeah, definitely I will.
It's a little bit more complicated, but anyway, I hope you all enjoy.
Sure. Yeah, sure. Thank you so much.
My pleasure.
Yeah. Are there any more questions? Yeah, I have one question, although I don't know it is making any sense or not. No, actually, instead, what is the main interest of studying this whole thing for L1 norm? So, is there any generalization of this notion, this whole thing? Why?
Good question, but I think we were motivated to try to do this, as I mentioned, actually, from this particular paper. When you can see, when we wanted to prove this last estimate, it turned out that we are working on the interval 0 to 1, and we were, as I just mentioned you on this infinite semi-Poisson problem, if we were able to control the difference between those h1 and h2 that came in that problem in with the f of u, we because of the delta rho going to 0 and delta rho tilde going to 1 as lambda goes to infinity, we were able to see that we can control the difference between h1 and h2 in the L1 norm. So then we look to see whether there is a comparison principle that we can compare it in that particular case. So this comparison principle was driven by this problem that we were studying. So there are other, I don't know, there could be. Did I answer your question?
Yeah.
And you can also see, I think I know that there are a lot of PDE people here as well. You can see this comparison principle is just done line on the one-dimensional case.
There is a question in the chat box. Rambanam, just next to that question. There is a question in the chat box, please.
My question is why we always work with the Laplacian having negative. Okay. Okay, that's just there's nothing serious about that. You can switch the minus sign on the Laplacian and put the sign on the other side if you want to. That's just okay. That's a question that let me share it again. Why doesn't it? Okay. You're asking a question like why we write always minus Laplacian of u, right? That's what your question is, not Laplacian of u. it doesn't matter, right? You are working always with something like that. So if you prefer to work with Laplacian of u, then it will be another h tilde, if I understood your question. But why do we work with minus Laplacian of u? It's just a nice habit for people who like, because when you have great rho, if this is equal to h, and if this is h is great rho equal to 0, and if u is equal to 0 on the boundary, then very nicely the maximum principle also, all these great rho equal to 0, and actually you can even have u is great rho equal to 0. All these, so the basic idea is that, oh boy, you have great rho equal to 0, great rho equal to 0. Then if you keep it with the minus Laplacian, then it nicely comes out as u is also great rho equal to 0. They all go in the same direction if you have it the minus Laplacian. If you work with a Laplacian, it gets switched. I don't know. That's about all I can tell you. So no, you can work with you don't have to keep the minus sign on the Laplacian. You can push it to the edge. Did I answer your question?
Yes, sir. Thank you. Thank you, sir.
Rambaram, you wanted to ask something.
Yeah. So, sir, actually, when we work with the Laplace equation, Poisson equation, Laplacian u is equal to f. Where f, then there is a maximum principle which says that if the classical maximum principle says that we can control the solution, sup name of the solution with the right hand side f and the boundary values.
Yeah.
But there is another maximum principle which is called Alexandro-Beckelman-Pucci maximum principle, which says that we can control the supremum norm of u with the Ln norm. N is the dimension there.
I see.
Yeah. So in this particular example, if we look at that problem from that perspective, so one is just matching with the n, because we are dealing with the one dimension case. So is it different from that?
But the only issue is that it's not the maximum principle that we are looking at. It's the comparison principle is what I was looking at, where the two right-hand sides are not comparable. Then can you still compare the solutions in a certain way? So it's not the maximum principle by itself. It's the comparison principle that this talk is about. So you have minus h1 and an h2. So if you want to apply the maximum principle, again, whether you use the other one or not, if the h1 and h2 are not ordered, then you have a question. Does it make sense? Do you understand what I'm saying?
Yeah, it is not ordered, but if we are comparing the Ln norm in the Laplacian equation, so that is also not ordered, I think.
But you're talking about a single equation, or you are talking about the difference?
Even if we have a difference, suppose we have the two equations and we are comparing f1 and f2. So there f1 and f2 will be subtract, then we get right hand side f1 minus f2. Then
h1 minus h2, right? Yeah,
h1 minus h2, and then the supremum norm of h1 minus h2 will be some less than equal to some constant type Ln norm of Ln. N is the LP, so P is equal to n. There n is in the dimension of the space that we are working with.
And then
f1 minus f2. So there is, I think.
Then what is the conclusion?
The conclusion is that whether it is a new one means it feels me that it is
It's a conclusion is something to do with. So you are talking about something like minus Laplacian of u is something, and you have some control on that. And what is the conclusion? Is u is greater or equal to 0? What is the conclusion?
That says that the supremum norm of u is controlled by the Ln norm of f.
Yeah, but how do I compare it? Yeah, my question, as I mentioned to you, I mean, there might be something good coming out from there, but our problem, what we faced here, is about there are these two functions that we had to compare to get that estimate. So we were looking for a comparison. So
yes.
You see, I had to come up with that u1 to be greater or equal to some 1 minus epsilon times u2, and then I controlled that epsilon naught to get my distance function. So that was the story. So it could be something worthwhile looking at. Maybe there might
what I feel is that while we prove the C alpha estimate, So it is little bit technical, but there also we get the level set, the measure of the level set. So there we get the same kind of quantitative estimate that you obtained here.
I see. I don't know. I did not look into that because number one,
So the important
we
thing
were
is
looking at
that
the one-dimensional situation here. Yeah. So go ahead. Yeah.
Yeah, you got a quantitative comparison. That is the main thing, and that gives their oscillation lemma, I think.
I see. I don't know. I've not
Because
looked into that Ram Baron. Is that right? Ram. You go as Ram or Ram Baron. I don't know. Ram. Yeah, I've not looked into that at all. Ram. I'll look into that. Yeah. That might be something worthwhile going towards higher dimension.
Yes.
Yeah.
Yeah. So I feel that I don't know. Means I thought that we got something.
Yeah. So I don't know yet. I have not looked into that. Any other
Are there
questions?
any- Yeah. If this is not the case, please let's thank to our speaker for the beautiful talk and the presentation. We are very happy to have you in our distinguished lecture series. So
Thank you very much for having me and giving me this opportunity. I
distinguished
enjoyed.
Yeah.
Thank you, sir. Thank you for a very good talk.
Thank you, and look forward to seeing you all maybe when I come to India next.
Yeah,
we'll
sure,
be very
sure.
happy.
Yeah.
My last international trip was to India in, I think it was in February of February of
it is on January.
2019. I think I met Dania in Goa, right? Dania. Is Dania still here? She's not here.
No, she's not here. Yeah, but I think
she was in Goa at that time.
yeah.
That was my last international trip. I've not done anything yet, but hopefully this COVID situation will improve so that probably I can see you all face to face. Thank you very much.
Yeah.
All of you all have a great evening. For me, it's a great the day is just
Thank
starting.
you, sir. You are welcome to our university when you are coming to India.
I'll be more than happy to visit you all. Thank you very much. Bye then, everyone. Bye, Sharad. Bye, Mohan.
Yeah.
Bye, everyone.
Yes, I would like to thank all the participants and our ITCAM people for conducting this session very smoothly. And one announcement: those who are interested to have these slides, the slides are available with us. You can contact me or my colleague Mohan. And especially also, I'd like to thank Mohan for taking this initiative. And thank you, Professor Shivaji, being agreed to give this talk in our lecture series. And as you said, that I will be very happy if we have it physically in our campus when the COVID situation is normal.
Oh, I love to do that. I've never been to Hyderabad, so that will be a good reason to visit Hyderabad.
So now this stage is yours, Mohan. If you want to have more chat with Professor Shivaji, you can continue.
Okay.
Mohan.
Hello.
Mohan, are you there?
Yeah, I am there. I am here. Yes.
Are you doing well, Mohan?
Yeah.
Everything going well?
Have more chat with
now. Hello.
Yeah. Mohan, I'm here still.
Yes.
How do you pronounce your name? Sajjad Biswas? How do you pronounce your first name?
Yes, Sajjad.
Sajjad. Or Sajjad.
Yes,
okay.
Sajjad. Yeah.
Okay.
Hello.
Yes.
So this problem we are doing for exterior ball when our solution is in a radial condition, right, sir?
Right.
So when we have a non-radial case, so how we will approach this one?
Well, this is a like, if you talk to Lakshmi, Lakshmi,
Yeah.
Lakshmi and Pavel has done some work on non-radial stuff.
Yes.
For the sublinear problem, but not on the uniqueness side, but more on the existence side.
Yes.
So I mean, naturally, you cannot bring it back to an ODE. You have to keep it in the exterior domain itself and work there. But there are sub and super solution theorems that Lakshmi and Pavel Drabek prove. So you can look at their paper. That's about all I know. And Lakshmi and her student, Anumal, and also I've recently done some nice work on some superlinear problems.
Yes, I know.
That's a recent paper which you probably are already aware. It may have not been published yet, but it's already accepted, I think.
Yes.
So those are the only directions that I have seen on the semi-positron problems.
Okay.
On the positron problems, I have a paper with Pavel Drabek and Maya on some S-shaped bifurcation curves on exterior domains. I mean, so there is some work, but there's a lot more work that needs to be done, and it's a very tough. You have a very tough. You're asking me a very tough question because we don't know whether the solutions are even radial. There's no reason to believe that when you're on an exterior domain, Gidasni, the ball condition is that you don't have that property. It's exterior. Yes. So it doesn't mean that positive solutions are radial. So definitely there are non-radial, could be non-radial solutions and things like that. So, but if you assume that they are radial, and if you have some restrictions on the P versus the dimension, then you can use this Kelvin transformation to bring it down here.
Yeah.
And so this is the problem. Of course, when you bring it down, Mohan,
yes,
it is a standalone ODE problem. It has nothing to do with the exterior problem, like minus U double prime or minus. It's a ODE nice problem. It's also applicable to the what? Radial solutions of the exterior domain problem. Otherwise, it's a problem by itself. I mean, that's a nice ODE problem, differential equation. So that's what we are studying right now. That was what was studied here, even though it's nice to connect it to a exterior domain PDE problem, but they are standalone ODE problems, boundary problems. So yeah, so your question about exterior domains, non-radial solution is really, there's a lot of work that needs to be done. Very little is known. Especially, I don't know of any result on the uniqueness on exterior domain for non-radial solutions. Now, of course, if you show that in general it is unique, then it becomes radial because there are radial solutions, right? So if you take the exterior domain, but when you take exterior domain, Mohan, there are a lot of stories here. It could be exterior to a ball, or exterior to, if it's not exterior to a ball, then there's nothing to talk about radial anymore. True. But if it's exterior to a ball and you study in general solution and then you prove that it's radial, it's unique, then of course there are radial solutions, so it will become radial as well. So there's a lot of study that needs to be done in that direction. Like even Lakshmi's paper, very nice paper with Pavel, she talked about a general sub and super solution theorem that could give you existence in the exterior of any bounded domain. But to apply the conditions, she struggled. She could only apply it in a ball, exterior to a ball, because you need to have some estimates. So they were very hard to apply exterior to any general domain. The theory is there, but when you try to apply it, it was easier to apply it only in a ball. So there is still some work even there, right? Even if you go back to Lakshmi's and Powell's work, paper that I really like the paper, then you can see whether you can apply that in a semi-positron problem. Yes. When the domain is not a ball, exterior to a ball, but a general domain. So there are a lot of things you can, if you are interested in going further, you can. Yeah, you are very close to Lakshmi there, so you all can think about it. Maybe you need to talk to her because you don't know what more she's thinking right now with her students.
Okay. I'll see.
Good. I hope the talk was simple enough. I hope it was.
It's fantastic. It's fantastic.
You asked me whether I could talk about math biology, but even the math biology problems, as soon as I put the PDE in, and then it becomes very technical, right? In some sense. So I thought I'll talk about this one, which is non-technical. No, it's not. And the latter part is a little technical, but the first part is actually calculus 1 based. The way I brought it down. That's what. Yeah. Okay, Mohan.
Vijay sir, you want to say something? Yeah. Okay, then Shivaji.
Okay, Mohan, have a great
Yeah.
evening. I also need to go to get ready for graduation ceremony and things like that.
Okay.
Today I have one PhD student that I need to hood. There's a graduation. Amila Muttanayaka, he graduated last year. Last year means last summer, but the graduation ceremony is now because he's now actually doing a postdoctoral position with Chris Costner and Cantrell.
Oh, great.
Oh yeah, so he got a very good postdoctoral position. So he's now working in Miami with Chris Costner and Cantrell. So which was very, very good. So he's here for the graduation ceremony. So I'll do that and do a little bit more grading for the day. I'm finished my exams, but I had to put the grades by Monday. One class I finished, but but other class I need to. Anyway, Mohan, I hope to see you guys soon in India.
Okay.
Hope these new variants and all die off. So that I'm fully vaccinated. I even have a booster, so I'm not too worried about it. But the travel restrictions are kind of up in the air. We don't know what if I go out of the country, then coming back, all these restrictions are kind of really not worth sometimes taking the trip. But yeah, we need to start. I think life needs to move on. I hope things get better. And
Yes,
all of you all take very good care. And thank you very much, Mohan, for the invitation. But there was some email about the initial correspondence said something about something that there was some honorarium or something. I don't need one. So please donate it to someone, okay? If you need one, okay? So just want to let you know that, Mohan. Don't just give it to a math club or whatever that you all want to do, or just give it to some charity if you all have to give it to someone. Okay, see you all later. Bye-bye.
Bye-bye.
Yeah. So Mohan, then I am closing the session.
You can close now.
Okay.